Hello, operating systems people. Today we're going to be continuing our discussion about memory allocation strategies and talking about two specific techniques, the BuddyAllocator and the SlabAllocator, that are pretty pervasively used in a lot of different contexts and are really, really cool. So hopefully you think so too. We will see. A lot of these allocators like Buddy and SlabAllocators, they're relatively specialized, and they're really pervasively used in things like operating system kernels. And that's because you essentially have this big array of bytes that is the physical memory on the system, and you have to not just answer the question, how do I allocate memory? You have to answer the question, I have a fixed amount of memory. How do I partition that up into chunks of different sizes for certain malloc requests? And then additionally, you have the case that you might want to allocate some memory that you want to map up into a virtual address space of a user in response to an mmap request or an sbreak request. Those need to be on in chunks, which are called pages of 4 kilobytes. So they are 4096 bytes, and they are 4096 byte aligned within physical memory. So we need to have some allocator that understands all of those constraints, and malloc does not, right? Malloc is not something that actually does all of that. It assumes that you essentially have an infinite amount of backing memory, and it assumes that you're allocating arbitrary sizes. So we need something a little bit more specialized. One way to think about that is simply that we could imagine there being a bitmap. So a bitmap is just an array of bits, where each of the bits, for instance, corresponds to one of those 4096 chunks of memory, each of those pages. And it could be 1 if it's allocated, 0 if it's free. So if we want to allocate n pages, then we just need to scan through that bit array one entry at a time, trying to find n contiguous bits that are set to 0. Once they are set to 0, great. Then we just go through, set them all to 1, and we've done our allocation, right? We find the corresponding pages and return them. But you have to ask yourself, what are the costs of this, right? Everything's a trade-off. This is really simple. This is really nice because there's going to be relatively little external fragmentation, because you're just finding kind of the perfect hole for your allocation. There's going to be relatively little internal fragmentation because you're able to allocate n pages if you want n pages. But what's the cost, of course? Think about it a little bit, pause, come back. Of course, the cost here is just that it's O of 1, right? Going through the bitmap, it is actually going to be pretty fast because going through a bitmap are actually usually machine instructions. Return the lowest non-zero value within a word, for instance, that give you the offset very quickly of a 0 or a 1 within a word. So you can actually do this relatively quickly, but it basically runs at the speed of just iterating through a big array with a whole bunch of words in it, right? Which, if we're talking about gigabytes and gigabytes of memory, is not that fast. It's not a cost that you want to pay on every single malloc and free, right? So what do we do? Generally, we come up with different techniques that make trade-offs, and the BuddyAllocator is a memory allocator that makes a trade-off that it can work within a finite amount of physical memory. So if we have 8 gigabytes to manage, it can split up that 8 gigabytes in response to different requests of different sizes. It works on a certain granularity, so by default it assumes a page granularity, 4096 byte granularity. So it allocates basically a multiple of that. And even more specifically, it's an instance of a power of 2 allocator, so it will allocate 1 page, 2 page, 4 page, 8 page, etc., right? So all power of 2 sizes of memory, down to 4096 bytes. So it's kind of checking off a lot of those requirements that we had for this kind of specialized environment, right? And how it generally works is that we're going to take a large range of memory that's not broken up into different allocations. It's all available for us to satisfy an allocation with, and we're going to recursively break it up into subsequently smaller power of 2 allocations, keeping track at every point which ones of those allocations are available, allocated, etc., right? So the big question is going to be, what are the downsides and benefits of this? Penny's already waiting with bated breath for me to go through the actual sequence of how BuddyAllocator works, but I want you to keep in mind, of course, that we're engineering here, so there are trade-offs. Keep in mind what they are, right? Okay. So let's assume that we have a request for the BuddyAllocator to allocate a 14 kilobyte chunk of memory, right? This is a power of 2 allocator, which means we always round up to the nearest power of 2 that's appropriate. So in this case, we aren't going to try to ask the buddy for 14. Instead, we'll ask him for 16 because we know that's a power of 2, right? Okay. So the first thing that it does is it says, I have all of my memory available. What we're showing here is that at the top, we have how the BuddyAllocator currently looks at that range of memory. Right now it's all purple, so it sees it all as available. At the bottom, in the dotted purple outline, we see just kind of a flat depiction of all of the memory and the state of the different pieces of memory. We won't update that for a while. So we want 16 kilobytes. 16 kilobytes is much smaller than 256 kilobytes. Certainly it's not within the power of 2 range that would require 256 kilobyte range. So we break the 256 kilobyte memory up into 2 chunks of half that, 128 kilobytes. Again, 128, much larger than 16. We break it up again. Notice that at all points, we're tracking the chunks that are actually available at this point in time, right? So we have the 128 kilobyte chunk of memory that could satisfy future allocation, and now we have 264. We're going to use one of them by breaking it up, and then finally, we have our 16 kilobyte chunk that we're allocating. Now you can see that appears in the memory at the bottom. We have actually allocated it out, and we're tracking these 4 other purple allocations as available for future memory requests, right? So this probably just kind of looks like power of 2 stuff. It doesn't necessarily look that interesting, but let's dive a little bit more into details. So if we then got a request for 70 kilobytes, well, we can't fit that in a 64 kilobyte request, so we have to fit it into a 128 kilobyte request. So we round up to the nearest power of 2 because BuddyAllocator is a power of 2 allocator, and because we have a chunk of that size, we can actually allocate it out for that request. And now you see in the physical memory at the very bottom where our allocations are being made. Okay, now we get a request for 90 kilobytes. Now, if you look at the system, we actually have 64 plus 32 kilobytes contiguously together in memory. So if you're just looking at physical memory, you would think that you'd be able to allocate that out, right? But the reality is this is effectively a power of 2 allocator. It tracks power of 2 chunks of pages put together, right? So we actually cannot make that allocation simply because it doesn't fit into the 64 kilobyte allocation or the 32 kilobyte allocation. So that request at this point would actually fail. And of course, all memory paths have to have logic that deals with failure, right? You can imagine, of course, a system is going to have much more than 256 kilobytes of memory. So you can imagine that there might be multiple of these ranges, or that, the top range, 256, which I chose somewhat arbitrarily, is actually something like 4 gigabytes, right? And we subsequently break it down more and more, right? Okay, so let's think about the trade-offs here, right? How expensive is it to actually make an allocation? Well, if we look at the structure of this, it's kind of, we're breaking it down powers of 2 each time, right? So we're going to approach the power of 2 size that we want after a logarithmic number of steps in the total size of the memory, right? So it's gonna essentially cost us some form of a logarithmic cost to do this kind of break up as we go down the BuddyAllocator, right? So it's not O of 1, but log n is pretty good, right? But we already learned about power of 2 allocators where everything was O of 1, right? So what the heck? Like, how is this possibly motivated? Well, those O of 1 power of 2 allocators, they always had to answer the question, how do they get the backing memory to populate one of those free lists of a certain size, right? And that's not simple. If we just need to ask the kernel for more memory, as was the case in the last lecture, then that's a simple solution, right? We just ask for more memory if we need it for a certain power of 2 size. But here we don't have that luxury. We're only given the total amount of physical memory in the system, right? Okay, so the issue here that we've kind of run into, we see this as log n. It's not quite as good as the O of 1, but it's much better than O of n, of course, log n. So, but we're kind of seeing a problem here that if we want to allocate a 60 kilobyte chunk, we can't because of this constraint that we need to satisfy it within one of these power of 2 slots. So the BuddyAllocator is essentially telling us how to populate the power of 2 free lists, right? But because it's a power of 2, we have this problem where it makes it more difficult to provide higher order allocations. And we conceptually touched on this a little bit with power of 2 allocators, and when we essentially said, how could you coalesce different chunks of smaller granularity, let's say 16 kilobytes, into one larger chunk of 32 kilobytes at the next highest power of 2, right? And I left that a little bit ambiguous as something that might be a little difficult, right? Indeed, it is really difficult when you cannot have headers within the memory. And a BuddyAllocator tends to never want headers within the memory because the memory that we're allocating out needs to be strictly a power of 2, not a power of 2 minus a header size, right? So whereas in the previous lecture we might have been able to say, well, we might be able to use the header to see if we can coalesce, in this case we really can't, simply because we don't really have any headers, right? So it becomes a little bit more difficult. Now, we still want to be able to satisfy larger allocations, which means we want to be able to coalesce in some way. And we see that when we actually go through and execute some sort of a free operation on that 16 kilobyte chunk that we previously allocated. When we deallocate a chunk, we turn it back into one of these available chunks, and the BuddyAllocator gets its namesake from the fact that a newly freed allocation will look at its buddy. So this is either the power of 2 allocation directly before or after it, whichever one is its buddy, right? Its corresponding power of 2 allocation. You see, in this case, it's the one to its right. And if that is also available, we can coalesce them together into an allocation of the next highest size. And of course, in this case, it does it recursively. So we can see that we have 232, it'll coalesce, we have 264, it'll coalesce, and there we're done. We can't coalesce anymore because in this case, the buddy for that allocation is allocated. Therefore, we cannot coalesce them, right? So this is effectively the idea. Now if we get a buddy allocation for 90 kilobytes, which of course we round up to 128 kilobytes, we can now satisfy that. So even though we did allocations of very small sizes, we're able to coalesce them very efficiently back up to a large size for a future larger allocation, right? So again, what are the benefits of this? What are the downsides? Benefit, we have very good coalescing. Downside, everything looks like a logarithmic operation, right? But as we'll find out at the buddy level, it's okay to have these logarithmic operations. We don't typically use the BuddyAllocator as our malloc replacement. We use the BuddyAllocator as the sbreak or mmap replacement. We use a faster allocator to allocate the different requests that we're making, and they ask the BuddyAllocator for the larger chunks of memory, right? So you could imagine sbreak being implemented with a BuddyAllocator, for instance, right? Okay. Now, how might we implement this is the next question. And you may already have some sort of a premonition. You might be kind of, your brain might be getting tickled from the lecture last time, where we're essentially saying, well, you know what? I mean, we can use power of 2 FreeList to track allocations of powers of 2 so that we can do those allocations very quickly. Right? So all of these purple slots within the BuddyAllocator, those are power of 2 allocations. There could be many of them of a certain size, and we might add them onto the different free lists and do allocations using effectively the power of 2 constant time allocator. So in that case, if there's an item on a certain free list, that's great. We can do an allocation from that bin very quickly in O of 1. If there's not, however, we might need to go to the next highest entry, figure out if it has any items within it, and then allocate one of them and do the buddy allocation thing of breaking them down into their constituent pieces. And what this means is that, yes, we can have very quick O of 1 allocation with the power of 2 logic that we talked about before, the power of 2 free lists. But we are going to be adding and removing things to FreeList relatively frequently as we create new sized allocations due to the buddy splitting and coalescing, right? So what is the cost of allocation? Well, worst case is still n log n. We still have all of the overhead we talked about before with the BuddyAllocator. But best case now is a O of 1, right? And you might make the argument that the system might quite often experience that O of 1, right? Coalescing, also kind of the same, right? But it is a little bit maybe more complicated in a BuddyAllocator to figure out the size that you're actually deallocating and to perform the coalescing efficiently. Remember, our free list might be embedded into the memory. That's fine for a free list, but we certainly do not have a header to tell us the size of a certain allocation. And because we don't have a header, we can't assume that the first bytes of the chunks of memory are configured to be either a header or free list. Therefore, it's hard to tell whether it is free or allocated. So we actually can't use any of the techniques that we talked about before, essentially about embedding some of the data structures within the allocations, except for the free list. That we can use, but that's about it. So we're left with a lot of problems here. How can we find the buddy? How can we find if the buddy is allocated or not? And then how can we coalesce up? And what is the data structure for tracking all of that operation, right? Now, the first thing that I want you to think about is that we are actually managing a finite amount of memory, the physical memory on the system. Therefore, we should be able to statically allocate a data structure that has a bit for each of the pages in the system. And even more, it might have a bit for each of the granularities of allocations for the SlabAllocator, which is effectively what you see here. And this is not a complete bitmap. There might be more bits further down for 8 kilobyte and 4 kilobyte allocations. So think of this as a partial bitmap. So the question is effectively, how can we figure out when we are freeing a certain allocation of size, let's say in this case 16, how can we figure out that its buddy is not allocated and therefore we can coalesce? And how can we tell how far up we can coalesce and answer that question recursively of whether the buddy can coalesce with us or not, right? So what's shown here on the left is a bitmap that corresponds to the structure that we see on the right. There is a 1 set when we essentially have a certain region of memory of the size corresponding to the level in the bitmap that has been allocated out. So at the top level, we essentially have 1 bit, 0 or 1, for whether that 256 kilobyte range has been used for an allocation. It's been used for 2 allocations, the 16 kilobyte and the 128 kilobyte one. We go to the next level of granularity and we have a bit per 128 kilobyte region, and we can see that both of those are 1 as well because there is an allocation in both of those chunks of that size. We keep going down and we start seeing that we have some zeros. The far left zero at the third level, the 64 kilobyte level within the bitmap, is 0. And that's because that 64 kilobyte chunk has not been allocated out. It's not used and it is available, right? So we follow this through and you see the bitmap configured as it is. And if we get that request to free a slab allocation, we might pass in the size that we're freeing or we might not. But whatever we do, we kind of find the corresponding entry in the bitmap for that allocation. In this case, that's what the arrow points to. We find its buddy in the bitmap, which is what kind of the highlighted, bolded boxes indicate. Those are the two buddy allocations. And in this case, because we are freeing the one, we are now going to be setting both that one to 0. Therefore, both of them are going to be set to 0. Because they are both going to be free, they can be coalesced up. When they're coalesced up, we again look at the buddy bit and see whether we can, after setting this one to 0, coalesce them both. And of course, in this case, we can. And we keep following that logic up until we see this. So effectively, all of that logic that I went through before about tracking allocated and available, we're just doing that with the bitmap, right? So if we implement the buddy allocator, with the bitmap here, we're again paying costs, right? Now we have the ability to have the coalescing logic work without having to have headers within the actual data that we're allocating, right? You can imagine, I want to go back to that just for a second. I'm sorry, this is slightly disjointed. But one of the important reasons that we want to not have a header in an active allocation is because if we want to allocate 16 kilobytes and map it all up into memory because user level just did an S break with 16 kilobytes, well, yeah, we can't have a header within that memory because then the user level would have access to that header and could corrupt it easily, right? So yeah, we can't have headers within the memory. Therefore, we have to have this bitmap to track which regions are allocated or free and at what granularity, at what power of 2, right? Okay, so then the question is, what are the costs of this mechanism? And the cost of allocating, we've kind of already gone through. The cost of deallocating, now we saw that it was logarithmic, but essentially we're just walking through the bitmap in this case, right? And setting values from 1 to 0 and coalescing corresponding to if two buddies become 0 at the same time, right? Now, this is wasting some memory. It's not wasting the memory that we used to waste for headers, right? But we now have a bitmap that is actually taking up memory. So the question is, how much memory is this bitmap itself wasting? Think about it for a second, try to come up with an answer, pause the video, come back, and we can talk about it. Okay, so how many bits are there? You can really ask yourself, how many bits are there for the finest granularity of allocation? The finest granularity of allocation is 4096 bytes, okay? So we need a bit per 4096 byte per page within the system. So that's 1 bit per page. Because a page is 4096 bytes, it's an immensely small amount of data, right? So 4096 times 8, because that's bytes, right? So times 8 is 1 over that number, amount of memory that we're wasting, right? So this is an immensely small amount of data, right? So the initial bitmap at the lowest level in the bitmap is A-okay. That's wasting no memory whatsoever. What you want to ask yourself is, we have essentially what looks like a binary tree here, right? How many nodes are in a binary tree when you know that there are n nodes at the leaves, right? And you have a kind of complete binary tree. Think about it for just a second, pause, come back. So we have n nodes at the very bottom. How many additional bits are there within the rest of the system? Each of these bits would kind of correspond to a node in a binary tree, right? Well, if we look at the second to last level, it's half the number in the last level, right? And then the next level above that, it's half that. In the next level above that, it's half that, etc., right? So if you add up all of these together, it's effectively 2n. So we're essentially wasting 2 bits per page within the system for the bitmap. That is immensely effective, right? That's essentially 0 memory whatsoever, right? So that's amazing. So this is a really cool technique, a BuddyAllocator for managing a fixed amount of physical memory that does so with logarithmic complexity in the worst case and O of 1 in some cases if you want to use the FreeList, but you don't need to. You could actually use the bitmap alone. Though it could get a little expensive. Okay, so the BuddyAllocator is one option, but it is very restricted, right? The BuddyAllocator only satisfies power of 2 sizes, lowest of 4096, and that alone is kind of a killer, right? We want to do small allocations that are very efficient. We require O of 1, kind of expected time. Maybe not worse, because we might need to ask a BuddyAllocator for more memory, but assuming we don't need to ask a BuddyAllocator for more memory, we want it to be O of 1 cost. And a SlabAllocator is the most common way to do this. And we'll see later that SlabAllocators are used everywhere from the Linux kernel, I can almost guarantee almost any operating system kernel, all the way up to actual malloc implementation. So we'll actually see that this, though it's very specialized, scales up to malloc. What SlabAllocators do is they kind of add another dimension to the trade-offs that we've been talking about. We talked about the amount of fragmentation in the system, therefore the amount of wasted memory. We talked about the cost of allocations. All of these things were part of the trade-off matrix that we were talking about for different allocators. Power of 2 versus first fit, etc. The Slab adds another dimension, and that is the API. The BuddyAllocator did this slightly too. It said, I'm going to make the API more restrictive. You can't allocate any size. You can only allocate powers of 2 with a minimum size of a page, 4096 bytes. Slab takes it a step further and says, what if we could make an allocator that is so specialized that it only allocates allocations of a specified single size? So the API looks a little bit like this. We have the allocation in the free function, SlabAlec and SlabFree. SlabAlec, instead of taking a size of memory, actually takes a slab. And free takes the slab that we are freeing onto and the memory that we're actually freeing. And now we get to slab create. I'm leaving out slab destroy here, but you can imagine what that does. Slab create, that's where we actually pass in the size of the allocations we want to be making, right? And that's often the size of a struct. And that will allocate a new slab. So now we have alloc, which takes that slab, and it knows the size of allocations it is allocating because the slab was created to only allocate regions of that specific size, right? So if we wanted to use this, you could imagine if we ported XV6 to do dynamic allocation of processes, we have our struct proc within XV6. We might allocate a slab for allocating struct procs. Therefore, it needs to allocate memory of size struct proc, so we see the size of there. And then when we want to allocate a new process, we just call SlabAlec with the slab proc as an argument. The proc slab, the slablet was allocated, and that is what allocates us a new process. And if we want to free that process, we have to free it back onto that specific slab. So you can see this is a very different API from normal malloc, and it's much more specialized to only the specific size, right? So because this is, you can almost really think of this as just like a free list of one specific size, right? So it's even simpler than a power of 2 allocator where we had a number of free lists, one for each power of 2. Now we only have one free list for the slab. So we have a single free list. That means it's exceedingly fast and it's very simple, right? It's O of 1. We don't even need to have kind of the constant time hand waving around looking through the array of all the powers of 2. No, we just know that the slab tracks a single free list. So we just look to see if something's on the free list if we want to allocate it. Probably a very simple linked list operation, right? It also has a massive benefit that we can actually implement this with no internal fragmentation, because we know the exact size of the memory we're allocating. So therefore, we can allocate the memory, the memory that we're trying to allocate, in effectively an array of that specific size. So, of objects of that size. So this is amazing. We got rid of internal fragmentation. It's O of 1, and it's basically as fast as you can get without a bump allocator. Super fast, super cool, really amazing. But, of course, this is super limited, right? This doesn't solve all of our engineering woes. It just solves one specific engineering woes. I want items of this specific data size, right? It doesn't perform coalescing across slabs. We just talked about a BuddyAllocator that does amazing coalescing across power of 2 sizes, right? And obviously it's not general purpose. If you want to allocate strings of a general size, right? This is often what malloc is used for. Yeah, this is not going to do that, right? But in a lot of applications and in operating systems, it's exceedingly common to just have certain structs that you're going to be allocating a lot. And creating a number of slabs, one for each of those structs, means that you have exceedingly fast and easy to manage allocation of structs of that size. And what we'll see is that it can cooperate with the BuddyAllocator for some of the coalescing. Okay, so let's think about a naive way to implement lists. We might think of slab create as just allocating kind of an array of objects of the specified size, right? So each of those orange objects in the array are of the specific size that the slab was created for. And we create this FreeList, which I've shown here. You essentially have the struct slab in the light orange, being the head of the FreeList, and we just have constructed a FreeList for each of the items in there, right? So, hey, this is like a simple SlabAllocator. I actually just implemented essentially the SlabAllocator for our system that can make assumptions about fixed sizes, right? So if we want to allocate memory of the given size, we get this call to allocate from the slab. Well, okay, we take an item off the FreeList and we simply return it from the SlabAlec. So now the darker orange or the reddish color means that we have an allocated piece of memory, right? So cool. Yeah, this is really fast, right? This is just manipulating a simple singly linked FreeList, right? Super duper fast, super easy, not a problem, right? Okay, cool. Notice it doesn't really make sense to talk about coalescing here because the slab only satisfies requests for a certain size, so you don't want to coalesce two things together, because then what are you going to do with an item of double the size, right? So it doesn't really make sense to talk about coalescing here. But there's kind of an obvious problem here. What happens when you call SlabAlec enough that you run into the case where, yeah, you know what, we can't actually do that, right? There's no more memory left on the FreeList. The FreeList points to null, so what do we return from the SlabAllocator, right? Now, what SlabAllocators do is they take each of these arrays and calls them a cache, okay? So we have objects, which are the specific things that we're allocating of the specified size. We have a cache, which is these arrays of those objects. And we have multiple caches for each of the slabs. So what this means is that we essentially add a FreeList per cache for each of the items within that cache. And then we have a FreeList of the slabs. Any slab that has a free item will essentially be in that FreeList. So this is maybe a little bit inaccurate because there should be a free item within this cache for it to be on that blue kind of global FreeList. So you can imagine this in this case just being a list of all of the caches for the slab. So when we kind of call SlabAlec, we don't find any memory. We can allocate a new cache, which you see has been done here. We can add it onto the list of all of the caches for the specific slab. And now when we want to satisfy an allocation, we simply need to find the first available cache that has an allocation. Again, we can kind of keep a conceptual free list of all the caches that have data in them, or free objects that are able to return. So now we have this O of 1 operation of finding the cache that has a free item in it and then removing an item from that free list to actually return for the slab request, right? So this is really cool. It still is constant time. Now we need to kind of go through what's conceptually kind of two free lists. One to find the cache that has a free item, and then the second to return a free item from that cache. But in the end, this is still amazingly fast. So now we have a dynamic allocator that is O of 1, has 0 internal fragmentation, but is relatively simple in how it goes about it, which is really cool, right? So this does raise a lot of questions, right? That we aren't coalescing here, but coalescing not only allowed us to create larger regions of free memory, so they could satisfy a broader range of future malloc requests, larger sized requests. But we also have this weird situation where, like, okay, so we don't need to coalesce, but we kind of want to give memory back to the system in some case, right? So we'll want to figure that out. So SlabAllocators actually raise a few questions. One of them is effectively, how do we allocate a new cache? And you know, I want you to think about this just a little bit, but I kind of already answered it, right? How do we allocate a new cache? I want you to think now a little bit more specifically, like what algorithm do we use to find a new cache that we allocate here, right? So think for just a second, pause the video, and then we'll come back. Okay, so how do you allocate a new cache? Yeah, we just talked about the BuddyAllocator. Most SlabAllocators have something like a BuddyAllocator behind them, or the kernel API for asking for more memory. So when we want to create a new cache, we can simply ask the BuddyAllocator to do that, right? But if we're asking the BuddyAllocator to allocate some new memory, we can see that we have a certain cache size, and that's effectively the free list at the head of the slab, at the head of the cache, plus the object size times how many objects are in the cache, right? So that's how much memory we want. But the BuddyAllocator allocates in a power of 2 starting at a minimum of a page, right? So the BuddyAllocator might allocate a slightly larger allocation than the size of the cache. And you can see that with the blue kind of remainder here, right? So the next question is, how big should the caches be? How many objects should we effectively have in a given cache? And we kind of want to consider the object size and consider buddy allocation sizes here. Think about this just a little bit. Pause, come back. Yeah, I mean, the most direct way to do this is just like think, all right, I could kind of do the math and take my object size, multiply it by different sizes, and see which one will come out with the smallest remainder with respect to the buddy allocation sizes. So if my goal is to minimize the internal fragmentation for a cache from the BuddyAllocator, then I could simply choose the cache size and therefore the number of items in a cache based on that. But that might end up with very, very large cache sizes. And one thing that we want to consider here is, when can we actually give the BuddyAllocator back the cache memory? The answer is effectively when all of the memory within a cache is not allocated. So when all of the memory in a cache is not allocated, then we actually know that we could return this cache back to the BuddyAllocator, and it could do all of its coalescing magic. The larger the cache size, the lower the probability that every single allocation will be free within a cache, right? So a small cache of size 1, you can imagine, like, all right, when we free that memory, well, we can return the cache back to the BuddyAllocator. But that's not that useful because size 1 means that there's going to be a huge amount of internal fragmentation from the BuddyAllocator, and it's kind of not really O of 1 anymore, right? Size of 2, well, we need to wait for 2 memory allocations to become free before we could give it back to the BuddyAllocator. So you can see we start having a lower probability of being able to give the memory back to the BuddyAllocator because some allocation might persist. And we don't really control that, right? So there's some pressure to keep the cache sizes relatively small because of that. So the prevailing knowledge is effectively that you want to make a trade-off here. You want it to be as small as it possibly can be without having too egregious a remainder in the buddy allocation size, right? So again, if we're targeting like a 12.5% memory fragmentation overhead, we might use that as our metric for choosing how many objects should be in a cache, and therefore what buddy size we should actually ask for. Okay, and then the last question is which cache should we allocate from? And we have multiple caches within our slab. Multiple of them might have free allocations. So this is a little bit more difficult, but I want you to think a little bit about which of the caches should we allocate from. And really what you want to think about here is caches that are mostly free or caches that are mostly allocated, okay? Pause, come back. Okay, so we have the two cases. We have caches that are mostly free, they have mostly free memory in them, and those that are mostly allocated. And we get a new allocation request. Should we make that allocation request from the mostly free or the mostly allocated cache? The answer is almost always that we want to allocate from the mostly allocated cache. There are two reasons for that. The first one is that we are trying to maximize the probability that all of the allocations in a certain cache will become free, therefore we can give it back to the BuddyAllocator. So we almost always want to make an allocation from a mostly allocated cache rather than a mostly free one, because we are increasing the probability that that mostly free cache will then get more deallocations, and we might be able to give it back to the BuddyAllocator because now everything's free within it, right? The second thing is that we want to optimize for spatial locality. Spatial locality is the idea that if we allocate a byte, the likelihood that we're going to access that byte or a byte close to it relatively soon is high, right? So if we access this byte, we're going to access a byte close to it soon. And this is kind of obvious from like structs, right? If we access one field in a struct, we're probably going to access another field, right? If we allocate an array and we access one of the indices within the array, we're likely to access another index relatively soon, right? So this makes sense. Now, if we have a mostly allocated cache, that means that we have a whole bunch of active allocations which are being accessed by the program. So the cache itself, the actual CPU cache, is trying to optimize for spatial locality in some sense. So therefore, we want to optimize the chance that our new allocation is spatially proximate to those things that are already being accessed, and therefore the probability that it will already be in cache is higher, right? So for these two reasons, optimizing for spatial locality and maximizing the probability that we'll be able to return a cache to the BuddyAllocator, we almost always want to allocate from a cache that is mostly allocated rather than mostly free. Okay, so we've talked about two allocators that are very specialized. One only allocates power of two sizes that are higher than a page size, so big allocations basically, but it can coalesce relatively efficiently and has log n costs. Then we talked about a very, very fast allocator, O of 1, and really for a fast constant O of 1, that can use the BuddyAllocator for its coalescing benefits while still maintaining the benefits of being very fast and having zero internal fragmentation, because we essentially have an array of the objects. But these are very specialized APIs, right? You can't write a malloc with these APIs. Or can you? The Linux kernel actually implements KMalloc, the kernel version of malloc, using the SlabAllocator. And what it effectively does is it creates n slabs, one for each power of 2, or, power of 2 with an allocation in between each of the power of 2s, or 3 allocations between each of the powers of 2. I'm not going to go into that. Some allocators choose slabs based on Fibonacci sequences. Like, it gets crazy. I'm not going to go into that. Imagine that we have n slabs, one for each power of 2. And then our malloc is just trying to figure out the next largest power of 2 for the size being requested, and then allocating from that specific slab, right? So if we get a request of size fs, then we want to round that up to a power of 2, find the corresponding slab that's customized to allocating memory of that specific size, and then allocate from that slab, right? So we're back to internal fragmentation, right? We have a lot of, I wrote external here, I mean internal. We now are back to internal fragmentation land. The difference between the slab size and the size of the allocation, yeah, that's internal fragmentation. Same thing as a power of 2 allocator. This is effectively a power of 2 allocator, right? But because the slab is so optimized, it makes a decent, effectively FreeList for backing a power of 2 allocator. So KMalloc within Linux is actually implemented this way. And uses a BuddyAllocator as its backing memory and coalescing scheme. So you can actually use both of these things, the slab and the buddy, together to implement malloc. And it's not uncommon. There are actually malloc implementations for user level that actually do effectively the same thing. So it's pretty common. Okay, so summarizing all of this, memory allocation techniques have a trade-off. We talked about this last time. Certainly it's in memory utilization. A common goal is to try to have 12.5% or less memory waste to internal fragmentation at the very least, but often to total allocation. We try to optimize for speed, having both O of 1 asymptotic complexity, but also fast constant times. But also there's a trade-off, as we've seen now, in the ease of use of using the API, or how general the API is. The SlabAllocator is not general, so it is trading off the complexity that you'd have from a general purpose malloc for being able to specialize around a specific size. Now, as with all of operating systems, we may use a certain mechanism or abstraction to construct higher level ones, and we've seen that with implementing malloc using the SlabAllocator. I also want to say here that there are a lot of trade-offs made in terms of parallelism, being able to effectively allocate memory on multi-core systems, but I'm not going into those here. Again, go to advanced operating systems if you want to understand that. And there's also really good documentation out there for JEmalloc, TCmalloc. These are awesome allocators that use a lot of these types of techniques to do their job, right? So GWU Alum is actually the lead developer on JEmalloc right now. So, this is definitely an area where there's innovation going on and where GW is awesome. That is all that I have to say about memory allocation. Hopefully your questions for this week give me some guidance on what was confusing, what was interesting, what you want to know more about. Otherwise, I will talk to you next time. Keep on operating systeming.